An important skill for a scientist or engineer is the ability to collect data and then analyze that data. Graphs are a common way to visually illustrate relationships within that data to allow for further analysis. Graphs can take data that's usually too numerous or too complicated to be described adequately in text and puts it together in a visually appealing way. With each set of data, you need to make sure that you're selecting the right kind of graph. For example, a pie chart is excellent to show parts of a whole. A bar graph are best to be able to compare things between groups, or especially when you have one data set that's numerical and the other that is non-numerical. In this particular example, we have, for Paul's plants, we have growth with 3 different sources of liquid. Line graphs are great for trends, tracking change over time, or being able to compare 2 numerical sets of data. Let's take a look at 3 examples of data sets and see if we can choose which kind of graph would be the best for each data set. With data set number 1, the graph would need to show the favorite type of movie that is appreciated by a group of individuals. Here, we could do parts of a whole. Out of all the people, what are the genres that are appreciated? So a pie graph would work for here, as well as a bar chart to be able to compare side by side the various appreciations for each movie genre. Data set 2 is showing us bacteria growth. It's growing over time. It's a trend. So in this case, a line graph would be excellent. Similarly, if we look at data set 3, we have multiple trials and we're looking at a distance of how far a rock gets launched with our slingshot. In this particular case, since we're comparing the distance to each trial, maybe a bar chart would work good here. So if you're going to produce a graph, especially a line graph, since that's going to be the main type of graph that we're going to see a lot this year in biology class, there are particular rules that you're going to want to follow. Rule number 1 is that every graph is going to need a title. The title is a descriptive explanation of what's being tested in the experiment and what data is being illustrated here. To be truly descriptive, it needs to indicate what was being tested and what was being measured. It has to show the independent variable and the dependent variable. You don't want to, have just a creative title like my favorite science project, because that doesn't really describe anything. We want to show what is being tested and what's being measured. So a real kind of fill in the blank example of a graph title is the effect of blank on blank. In the example that we did in class, a good title for your graph would be the effect of insecticide concentration on the number of cells with damaged chromosomes. Here we know that we're going to be able to observe how the different concentrations impacted chromosomal damage within cells. The next important rule is we need to make sure that we set up our axis and label them correctly. The axis needs to be labeled with the variable that is either being tested or measured, and then the units. Units are very important. There's a huge difference between an inch and a foot, a mile and a kilometer. In the case of labeling our graph, the manipulated variable needs to go on the x-axis. The independent, the one variable that is being modified by our experimenter, goes on the x or horizontal axis. The responding variable, or the dependent variable, the thing that we're measuring, is going to go on the y. A good gem of wisdom that you can use to remember this is the acronym DRY mix, which stands for the dependent variable is the responding variable and it goes on the y-axis. The manipulated variable is the independent variable and it goes on the x. So when we look at our experiment that we were graphing for our example, the thing that the scientists were changing was the insecticide concentration. So that needs to go on our x-axis. And if you see there, we have our units, which is ppm, which stands for parts per million. We've got our title, and then the thing that we're measuring, our dependent variable, which goes on the y-axis, dry, dependent on the y, that's going to be the number of cells with the damaged chromosomes. Now finally, before we start plotting our data, we need to make sure that we scale our axis. Now the scale has to include all of our data. Now the cool thing is each axis doesn't have to have the same scale, but you have to be consistent. One of the things that we have to remember is that a graph is actually a representation of a line. And we need to make sure that there's a mathematical relationship between our data and the line that's going to be produced. So the axis has to be consistent. If on the x we're going by 5s, then certain tick marks are going to equal 5. They have to be consistent. If we're going by 2s, we need to make sure that we're consistent. Another important note is you want to use the whole of the graph. Spread out your numbers appropriately so that essentially we're zooming in on your data. You don't want your data scrunched up in one little corner. So on my y-axis, I needed to make sure that my data spanned from my lowest number, which was 3, up to 30. And when I counted my tick marks, I found that there were 15 possible spaces. So to really use the bulk of my y-axis, the best way to space them out was to go by 2s. To keep my axis from being less cluttered, I didn't label every single tick mark, but I'm still consistent. Every increment is equal to going by 2s. Now on my x-axis, the concentrations went from 0.01 to 0.20. And of course, working with decimals can be difficult, but it's the same breakdown if it was a decimal or if it was a whole number. You can kind of imagine them as being like whole numbers, 1, 10, 20. So knowing the breakdown of my x-axis, I ended up making the major tick marks be equal to 0.05. And because there's 1, 2, 3, 4 of those tick marks, so I was able to accurately put those together. So then we're going to plot our data. We have to make sure that we accurately plot our data. Once it's plotted, the last thing is to be able to provide a trend line or a line of best fit, or in some cases, a curve of best fit. The determining whether or not it's a curve or a line is we have to look at the trend. What's going on? Does it look like it's curving? Does it look like if we could have a single line that would go through the majority of the points with, maybe a few being on either side? When you're doing your line of best fit, do not just connect the dots. We want to draw a line that's going to go through the majority of our points if it is a line of best fit. Also, make sure that your line stays within the boundaries of our graph. Now, sometimes when we're graphing and we begin to analyze the results, we'll find that some data points are going to stand out. We're going to call those standout points an outlier. These data points don't fit the general trend. Now, we might wonder, is this a bad piece of data? Is this, something that went wrong, an error that we did in an experiment? Well, the best way to find out if it's an authentic data point or just an anomaly would be to repeat the observations. Redo that experiment. Now, to minimize outliers, we have to make sure that we're doing careful measurement and that we collect enough data so that we can look at a particular trend and make a determination of whether or not that data point is indeed an outlier or not. Now, one question that sometimes comes up is, say we do have an outlier. What do we do with that when we're reporting our data? Do we just erase it? Do we pretend like it didn't happen? Absolutely not. We need to make sure that whatever data we collect, that it's reported in some way, because otherwise you're just hiding things that happened. If it truly was anomalous, it was a data point that you collected. So you might not put it on the main graph, but then you could have an asterisk that said, hey, there's a little bit more information that you need to know. We've excluded this data point because. So we're still mentioning that it was present because it was something that we collected. We want to make sure that we're reporting all of our data, and if we're going to say, if we ignore this data point, the reason why we're doing that is because we've determined XYZ. We've determined that it was anomalous. We don't want to hide data that we collect. Graphing is an important process. It allows for an accurate graphical representation of our data so that a potential viewer of that data can understand a lot of the experiment that you have explored, and to draw conclusions and to analyze a lot of information, to glean information from that particular graph. So please follow the main rules for graphing, choose the best graph, and we'll be much better data collectors and data presenters as we move forward throughout the year.